Hello everybody and welcome to session number 11 of my lecture on statistical energy analysis and hybrid methods. Today I would like to talk about plates. Why are plates so important? Because plates are thin structures and they are an excellent tool to create a technical system, a lightweight technical system. And this is why they are so important also for vibroacoustics. Good. So, nomenclature. A plate, we suppose that plates are flat and thin structures. And in contrast to this, a shell, you should not mix this up, is not a plate because the shell can be curved. Plates and shells are the most important structures in many vibroacoustic investigations because they provide a very high stiffness at low weight. Most means of transportation vehicles are created by such enclosures which are made out of plates and shells. So you see here in the figures, so this is a fuselage, which is definitely a shell structure and some plates in between. The same is true for a car body structure of a car, and also in trains where we very often use extruded profiles. You have something which is a system of several connected plates. Let's come to some assumptions that has to be made if we talk about plates. First of all, a plate has to be thin. If it's thick, it's not a plate. That means the thickness h is much smaller than all the other dimensions. So, for instance, the length in x and y directions. Here we just using a thicker presentation because otherwise you won't see any symbols. You have in-plane displacement, which is denoted by u and v, here just showing the u in x direction, but you have out-of-plane or orthogonal displacement denoted by w, which is considered as a displacement in z direction. All in-plane strains are supposed to be very small. There is no, we say that there is no transverse shear strain, so bending could be applied like this. But something like a shear strain, as denoted here by this figure, this is neglected for plates at the first extent, for simple plates. Any tangential displacement, so the in-plane displacement is a linear function of z. So this has something to do with the curvature, which is somehow obvious. So that means there's no complicated relationship between for the in-plane displacement with regard to the thickness. And last but not least, the transverse shear stresses at the surfaces, and all of them, so in z, x, z, xy, and xz, they are supposed to be 0. Good. So let's come to the next step. When we talk about plates and also shells, the physics is described that we're using only the displacement of the center plane. That's the middle plane of our plate. All other quantities, also those quantities, and especially the dependency of those quantities in z are derived by this from simple formulas. So as mentioned, assumption number 4, we assume that there is a linear relationship between the displacement, the in-plane displacement, and the thickness z, and this function is supposed to be f1 and f2. Good. So these are the tangential displacement or the in-plane displacement of the middle plane. And we can enter this into our stress-strain relationship that is well known. And we're using assumption number 3, meaning that the shear strain is supposed to be 0. And if we do so and apply the above formulas, we can easily find that the relationship between the function number 1 and the derivative of the out-of-plane displacement to x and y gives easily a relationship between those functions, which are as given here. So it's just the derivative of the out-of-plane displacement in x and y direction with a negative sign. So And the remaining stress-strain equation leads then finally to all the things that we know. So that means our strain, depending on the thickness variable x, is given by such formulas. So just the middle plane and a specific, let's say, relationship of the, let's say, the out-of-plane displacement. Why do we need this? We will later need this to describe all the mechanical equations by the middle plane quantities. Good. Now we will go step by step into the wave equations, and we start with the in-plane motion. For doing so, it's quite convenient to integrate over the plate thickness so that we have different quantities. So we switch from the stresses, which are forces per area, to quantities that are defined per length, and here denoted by m. So this is the force per length. And we get this by integrating typical stresses over the thickness. And bending would lead to symmetric stress, and that means by making this symmetric integration, there isn't these forces are decoupled from bending motion. So from the assumption that we say that sigma in z direction is 0, it follows that the formulas for the stress-strain relationship can be simplified. What does it mean? Normally in the solid material, there would be an additional expression for sigma and z, which is simply missing in this version here. So with the above equation here, and using again the Folk notation, we can now find the relationship between all stresses in x, y, and z direction, depending on the displacements of u and v in our plate. Why do we need this? We need those expressions to calculate the forces per length. And this is what we do in the next slide. So if we enter those expressions, we get this equation 139 for the force in x direction, and we can do similar things for all the other directions. Again, some of the terms in 135 vanish because we have the symmetry assumption. Good. So we have now collected all forces in per length in our plate element, which are denoted here by the given vectors. And we have now, we use an example, we create the force balance in x direction, which is this one here as denoted. And if we do so, we are ending up with the final force balance in x direction, which describes, which includes also the pressure on x, which is the force per x, an external force per x direction given by this. So if we divide this by the area of this plate element, we get two expressions for the force in x and in y direction. Similar to the thing that we have done for the solid material for the cube. So the cube is replaced by a small quadratic shell element here in this version. Okay. As a next step, in the here derived force balance equation, we use the above equations to they are entered here into this, and we show this for the x direction first, and then we get finally this expression here, and after some modification we are ending up with this expression for the force balance described in terms of displacements. So there is no more n anymore. It's just forces and displacement of the middle plane when we have skipped the indexing here. So the force per area is now equalized to the external pressure and the inertia forces, and that means it's a relationship. This is the inertia force, and this is an eventually available external pressure, and this finally gives the wave equation for the in-plane waves. We need the following acronyms, the constants C and S, which are just a function of the Young modulus and the thickness and Poisson constant. And then we get finally this set of equations. So this is the equation for U, mainly, but keep in mind there's also the v component. And the same can also be done in the y direction, which is mainly an equation in v direction, but also the dependency from the other direction u. So the motion of the in-plane direction is coupled. So displacement in u also leads to motion in v. I mean, similar to the full material, where you had shear and longitudinal waves. The shear wave is more or less the same in a plate. It does not change very much. It's just depending on the shear modulus. But there's a slight difference for longitudinal waves. If you remember the longitudinal wave in the solid, there would be no motion into the perpendicular direction. And the point is that there is no stress, so it's not constrained. So it could have some extra motion. However, we just choose that the wave propagates in x direction, and we say that there is no change in the direction of y. So this is why it is supposed to be 0, and also the displacement in the y direction is also supposed to be 0. With these assumptions, we can create a wave equation or find a relatively simple wave equation in x direction, which looks like that. And we know that this is supposed to be the speed of the wave speed, and it would give this equation here. It might look similar to other speed of longitudinal wave speeds, or it might consider it be a similar equation for the longitudinal wave state. And the thing is quite simple. So here we have just shown all the different versions. This was the longitudinal speed for solid material, which is larger than the one for plates, which is larger than the one for bars. The reason is quite simple. The more constrained the material is, the stiffer it becomes due to the lateral contraction. And that means by solid, plate, bar, we have a decreasing longitudinal wave speed. So the strain thickness can be easily calculated by using the stress-strain relationship. And if you do so, we would get this typical shape of the longitudinal wave in a plane. So far for in-plane waves. And now let's come to the bending wave equation, which are, as we will later learn, much more important for vibroacoustics. One typical reason is that bending waves describe the vibration in normal direction, and this is what can radiate sound in a fluid later on. We follow the same trick. We use moments and perform an integration over the thickness. And please keep in mind that there is a z. But this is what you need to create a moment here at the corners. And we have, and the moments are denoted by these small circular arrows showing that there is a moment at our new plate element. But there are not only moments, there's also the integration of the shear stresses, which gives a force in the normal direction at the plate edges, denoted by Q. And this is why there is no Z here. This is not used in this formula here, and using the shear stresses as a description. Good. So we're using several equilibriums to get to our equation of motions for the plate, for the bending waves. So first of all, we take the equilibrium of total forces in the Z direction, which gives us this expression here, just summing up all the forces in normal direction of the plate, which has to be, let's say, equal to the external force here at the plate. And the same can be done for the moments. I will not go too much into detail, so you can take this in the very detail out of my book or other literature. So this is the moment, let's say, just as an example, take the moment balance around the x-axis. So it's this moments that I used plus the moments that are here. And in addition, it's the shear stresses here in that direction, but using the leverage of the plate, because this also creates a moment, because there's always a lever available. And if we do so, we get those two equations that finally relate the Q's and the moment expressions. Again, neglecting terms of second order, And using a typical value for the moment equilibrium, we get the relationship between the moments and the shear stress here and the per length of the plate. Good. If we now enter the formula that we had from the stress, the forces and the forces per length in z direction, we can finally derive this equation here, which is an equation with just containing moments and an external pressure. So we have nearly achieved what we need to find finally the wave equation, but we have just some remaining steps to do. So first of all, we need to create, let's say, a formulation of displacement. And though again, we have to keep in mind that our bending motion is decoupled from the in-plane motion. So that means u and v are always zero. This comes with the symmetry. And that means that the strain relation of plates are just only linearly dependent of that. So that means our displacement, that's the typical expression that we have derived from our assumption number 5. So when we enter this into our classical stress-strain relationships, we got again the stresses for our in relationship just relating to the normal displacement, and there is no u and v that can be found. Please don't mix up. This is a Poisson constant. It looks like the v, but it is not actually. Good. So this is applied. If we apply this in the definitions for moment, I mean that's the integral thing, we get this relationship for the moment from and the displacement in the normal direction. Just to understand what is meant by B, this is the symbol that's used for the bending stiffness of the plate. So this is the stiffness that is defining how stiff a plate is for bending. It depends on the Young modulus and the cubic thickness of our plate. So if you double the thickness of the plate, the bending stiffness is quadrupled. No, it's 8%. So if it's just doubled, then you have 8 times the bending stiffness like the other plate. Okay. With the equations here and 145, which is the relationship that relates. Just go back to show you 145, which is just the equilibrium equation. We can finally end up with, we can express all the shear forces again also as a function of the displacement. So just to summarize this slide, that means all the expressions that we need for the description of the bending wave equation are now expressed in terms of the normal displacement. That was our goal at the end of the day. Good. So from equation 146, and with all this equation that we have gathered here, just to keep you in mind what was equation 146, that was the step, let's say, where we had all the moments related to the external pressure. With all these equations and using the relationship between the for all the moments and so on, we finally get the plate equation. So that means this is just the only, we have very specific derivatives of the normal displacement, and this has to be related to in somehow how defined external force. So in order to get a wave equation out of this, now we have to set the force per area pressure equal to the external pressure, some external excitation, whatever, to the plus the inertia force, which is the area weight and the acceleration of the plate in the normal direction. If we do so, we get this equation, which is actually a wave equation. There's a specific operator. This is this double plus operator. This has a specific impact that I will show you later. It makes the bending waves somehow complicated. Just in order to determine an idea about the wave speed, we just use the harmonic approach again. So we're using the exponential function to get an harmonic description out of this. And this would look like this, having somehow the similar shape. And if we're using, let's say, take the ansatz to use the typical wave motion for harmonic waves, which is supposed wave number, you will get the following expression for wave number and wave speed. So the wave number is also the fourth potential, which is related to the square of the frequency, angular frequency. And the wave speed is kind of special. So it's the fourth root, and there's a quadratic frequency dependence. That means, as a consequence, the speed of bending waves is getting higher and higher the higher the frequency gets. Which is, so it means now, for the first time in our whole lecture, the wave speed depends on the frequency. And this has a specific impact, as I will explain later. Good. How does a bending wave look like? So we can again write this in Helmholtz form. So using all the typical harmonic approaches and using the exponential function, it would look like this. And if we solve this for the wave number, we get two real and two imaginary solutions. We denote this by wave number B1 and B2. We have plus minus, which is clear. And only the real solution would create a propagating wave. So this is a complex wave number, means that at the end of the day, it's a evanescent wave, which is very strongly decreasing. That means if we have a one-dimensional solution, it would have 4 wave types. And if we're just using only the positive values, we would get those expressions here. Good. So another option is to write really 4 waves in all x directions, and this would look like this. So you already see things are somehow complicated. Again, the complex wave number would lead to an exponentially decaying wave. It cannot propagate. It will stop propagation very, very in a short length away from any source. Anyhow, we have found one specific effect. We have dispersion. What is dispersion? If the wave speed is frequency dependent, this is what we call dispersion. We have this very often in optics. You know that this is why we have color effects in prisms and so on. That's the same thing, because for light waves, that's the same impact. Here we have the same thing for our bending waves, which have this relationship between frequency and the wave speed. Good. Now let's come to a specific case that is worth investigating. We will talk about cylindrical bending waves. The question is finally, why are we doing this? You know, in order to derive coupling loss factors later in SEA, we need impedances. We need source impedances, similar to those things that I have described in the source description for fluid waves. And a cylindrical wave would be, let's say, radiated by a force that is exciting a plate, as it is denoted here. It will be a cylindrical wave propagating away from the force excitation somewhere in our plate. So we assume that the solution is totally symmetric, rotationally symmetric. So we also suppose that there is no rotation in the excitation, and we assume that the Sommerfeld condition is fulfilled. So that means this wave is decaying if it goes to infinity, and then it is vanishing in large distances. So we start with our wave equation and rewrite this a little bit. So our double Laplace operator can be used in this kind of binomial, and then we would have kind of 2 wave equations more or less that can be solved step by step. So we have a system of equations out of this, one with a plus and one with a minus here, and we solve them now once after the other. The first equation is very similar to the Helmholtz equation, like for fluids, but for 2-dimensional. And the 2-dimensional wave equation is solved by the so-called Hankel function of second kind. That means for our first solution, we will have any constant 1, C1, and this famous Hankel function. You will later see how this will look like. The solution of the second equation can be found in a similar. The only thing is we have to replace our KBR with the negative complex value. That means that would give the solution for this equation here, denoted by W2, and we call the constant here constant number 2. Good, so far so good. Now the next step is to find the constants C1 and C2 depending on the properties of the plate and our force. So for doing this, we need some asymptotic behavior. So first of all, we need an assumption or an approximation for the far field of the Hankel function, and this would be this one for large arguments. And we need something for small arguments, what we call the near field. And these are very useful for the further derivation. So this would be this expression here for the near field, for small x. So now we use the large far field assumption and for the second wave solution of the second wave equation. And that means we can approximate this using the above assumption, and that would give this expression here. That means, obviously, that the solution of the second equation, this is our exponentially decaying near field. So this is the one that is not really existing. So that means that we can use in the total solution, we are summing up those W1 and 2, which are shown here. So and the next step is now that we have another assumption. We say that the curvature of our solution, so the derivative, it must vanish in the center, obviously, because if there would be, it would be a singular point, and when we just calculate the curvature, we get this expression for C1 and C2. We have here the R on the denominator, and the only chance to fulfill the requirement that it gets 0 is that those quantities are the same. C1 must be equal minus C2. That means we have now, we got rid of one of the constants. So we have replaced this by C1, and that means our final solution is the combination of these Hankel functions plus the remaining constant C1. How do we get the C1? This will follow in the next step. Now we're using the other asymptotic expression. We use the asymptotic expression for the small values, which are just used here in this expression. So that means at 0, we have this formulation here. That means it's quite a simple one. So we see that the displacement at 0 follows this funny expression, lots of complex constants and pi's. And that means at the end of the day, this is C1. So C1 equals the displacement at 0. That's it. Good. So now we have the solution, which is crazy. Now the question that we finally need is, how can we relate this to the force? And in order to relate this to the force, we assume a small circle which radius are 0, and we consider let's say the stress per length in z direction, and this is given by the bending stiffness and the derivative of the displacement. So because now we have everything on board, because we know the displacement, we know the force, we know the relationship between Q, and this is something that helps to derive the relationship to the forces and to calculate the displacement at this point depending on the force. So if we enter all this here into the above equation, we get this expression. So this is just using all the equations that we have here. And this finally needs that again we use the approximation of the Hankel function for small arguments. And this gives the relationship between our Q at a specific radius and the displacement. And then if we just use the surrounding of this cylindrical disk, I mean, if we just integrating over the circumference of this disk, we can finally provide a force out of this. That's just easy. This is this circumference of our small disk. Now we have a relationship between our force and our displacement in the center. This is what we were looking about, because this is what we need to find a stiffness. The relationship between force and displacement. This is our famous stiffness. Good. So anyhow, we finally get the solution. So just have a look at that. So the displacement of a plate, and we make a cut and look into both directions, is looking like this. And you see that this also, you see why this C is minus and plus C2 is the negative C1. We just have provided depicted the solutions here. So the orange one, that's the first one, which is given by this. And the second one, that's the one that can propagate. But in the center, we need both, because they are really compensating each other with extreme values. And for different time steps, and if we add them up, we get the final solution looking like this. So this is the shape of the circular wave excited by a force, by the combination of those two solutions of the different wave equations. Good. However, the thing is that even though a plate equation is quite a complicated equation with dispersion and so on, the formula for the mechanical impedance is extremely simple, because that's the relationship of the force in that direction divided by the velocity in that direction. And this would be this expression here. So just the wavelength, wave number is part of this formula, the frequency and mass area, nothing more. So this is really quite simple. And this is also good because that helps us to easily identify the source characteristics of if some point like is exciting a plate. Also the far field, also important to know the displacement or the square amplitude of the displacement is 1 divided by the radius. So this is how the amplitude is decreasing if you go farther away from the point of excitation. Good. Again, why are we doing this? Please note, we need impedances to describe the coupling loss factor. And to be honest, this is the only simple impedance that I can get out of plates. In the lecture, you can also use some kind of radiation stiffness of the edges of a half infinite plate, but this is hard to explain in a lecture. And I would really recommend that you take a look at the book to get into the details of line junctions and so on. But for point-like things like here, the point impedance is very helpful and helps to understand how plate and other systems can be coupled. Good. Okay. Damping. The damping of wave propagation is related to transport of energy, and this complicates the treatment for dispersive waves because we have another dependency. And just keep in mind, an easy way to address this is to look at the complex Young modulus, because this is where damping is hidden. That's an easy way to address that. And this also is true for the bending stiffness. And when we introduce this into our equation for the wave number, we get, after some modifications, that it would look like this. That means the wave number is the fourth root out of this. And if we simplify this a little bit, we would get this expression here for the damping loss factor if we would like to investigate the complex wave number. And again, this is in contrast in the acoustic wave number, where it was 1/2. This is 1/4 of the wave number. So that means the roots are a little bit changing how to bring, let's say, the loss factor into the wave propagation of bending waves. Good. One last thing to describe is the famous dispersion and the consequences of dispersion. And one of the biggest consequences is the introduction of the group velocity that sometimes lead to strong confusion. So what is a group velocity? I think a very good way to explain this is to assume that we have a wave that is a combination of two harmonic waves, two frequencies, omega 1 and omega 2, and the related wave numbers k1 and k2. And they have the same amplitude, and then we can use some trigonometric functions which are ending like this. And if we rewrite the orange and the blue expression a little bit, we can define a kind of, let's say, group omega, which is more or less the difference between the two frequencies, half of the difference, and the same is true for the wave number. So, and the blue one is a kind of average. It's a mean frequency and a mean wave number. So this interference leads to a kind of carrier wave. So like in radio systems, so this is your high frequency carrier, that's the blue line. And we have an amplitude, which is the orange one. And this amplitude is modulating the amplitude of the carrier. The amplitude of the carrier is modulated by a lower frequency because it's just the difference of the frequency, which is much smaller. It could be much smaller than the mean value between those two waves. Just imagine that these waves are very near to each other. It will be a very, very slow frequency. So what is also obvious, that means the energy is proportional to the squared amplitude. So the energy is hidden in the orange curve. So this determines how the energy is given. But this also means that the propagation of energy is related to the wave speed of the group wave speed, or let's say the wave speed of the amplitude modulator. So again, it can be easily done. It's just what is the group velocity is just the delta omega and the delta of the wave number. And if this is getting very small, we can just, it's a derivative. So it's the derivative of omega with respect to k. So this is the quantity, the group velocity is the wave speed that describes the propagation of energy. This is something different than the speed of the wave speed, the phase wave speed. And just to visualize this a little bit, just imagine here, this is at time step 0. We would have this effect, and just have a look at here at this phase that we have fixed. The next time step, the phase would move like this, going to this place, and but the group has velocity is much farther. The group velocity is for bending waves is twice as high as the phase velocity. So that means the maximum of our energy is moving faster than the phase velocity. And if we go then to the next time step, we have the same effect. So again, the phase moves for the same step, and this is going even further. Don't be confused that let's say the direction has changed now. This comes from the fact that now the amplitude is negative because the phase has farther moved away. Very important for you, and this is very important for SEA. Due to the fact that SEA is about energy in wave fields, the group velocity is very important. That's much more important than the phase velocity. Good. Just to summarize, the speed of energy propagation in waves is the group velocity. When there is no frequency dependent of the wave speed, they are equal. So it makes simple, which is the case for fluids, acoustic waves. Energy travels with the group velocity, so that means our relationship for the intensity has to be modified a little bit. So the relationship between energy density and intensity is related to the group wave speed. Finally, just to give you an overview and to also, let's say, finally summarize how complicated the structural wave speed things are, just to give you an overview of several wave speeds of phase and group velocity in bars, torsional waves in bars, bending waves, longitudinal waves in phase, shear waves, which are everywhere the same, and the longitudinal waves in bulk materials. So you see, this is why structures are complicated. By even the simple wave speeds and simple structures, you'd have to understand how to learn lots of formulas. Good. So that's it for session number 11. Now the next step is we will go to systems. We will present systems, distributed systems, for instance, rooms, like shown here, fluid systems, then later plate systems and so on, to see how they behave in the low frequency range and to get the first step to the descriptions of SEA subsystems. I hope that you have fun and it was not too heavy, but please keep in mind, even though all this in-plane and out-of-plane bending motion of plates, it looks complicated, but unfortunately you have to understand that to master vibroacoustics, because this is the most important waveform that you need to design and do the layout of a vibroacoustic technical system. Have fun and see you later for session number 12.